Hey, what's up, guys? Yeah, so this is my second algebraic videos, algebraic geometry videos about varieties, and I hope you guys subscribe to my channel. Okay, so previously that we have already defined this Z map, which is zero locus. If you take subset of the polynomial ring, and the Z of this polynomial ring is just, for example, if you take T, and your Z of T just defined to be all the points in AKN such that f of x is 0 for every x belongs to T. Okay, now you can also take an ideal if you someone take a subset. Basically take subsets. Let's say you take another subset T, and then you can collect all the polynomials in the K of x1, xn, such that f of x is 0 for every x belongs to T. Okay, and so this video that I want to provide some their correspondence, and I think this is the beautiful part of this variety language. Okay, so the following is true. So some of them are very tedious commutative algebra. So sometimes I will skip and then make some other videos to fill out details. So T1, and you get a zero set. So what's the zero set? If you take the subset to be larger, the zero set should be smaller, right? So this should be trivial. And the second is that y1, y2 are subsets. Let's say are subset of an. Then obviously that akn is obviously that the polynomial that vanish on every point should be decreasing. Okay. Okay, and also if you take y1, y2 to be subset of akn, obviously that your union will just be the intersection. Okay, I think these 2 or 3 of them are trivial. So the first 5 are first fifth are very important. Okay, I think these 2 are key fact of this variety language. And so it's like for any ideal A belongs to, let's say, polynomial ring. So sometimes I will use A. Okay, if you take the Z of A, right? If you take the ideal, the zero set, and then you take ideal, definitely you will be this, right? But amazingly, it will be the radical of A. Okay, I will not prove this. This is so-called Hilbert Nostalgias. Yeah, Nostalgias. This is very hard to spell. Sometimes I never spell it correct. Nostalgias. Okay, so I will explain this in detail, but I will not prove this. So I will make another video to prove this Hilbert Nostalgias. Okay, so number 5 is that if you take subset of this akn, and you can take the polynomials, right? That polynomials vanishes, and then take a zero set. Obviously, that this will include y, right? But actually, this will be the closure of y. Okay, so number 4 is called the Hilbert Nostalgias. So let me explain. So so simply speaking is that simply speaking is just this. So we just if you Z of A, take this will be square root of I. So square root is called the radical of A. Radical of yes, this is called radical of A. So radical of A means that you take F belongs to somebody give you a polynomial ring R. In this case, will be this, such that FR belongs to A. Okay, this is somehow like trivial, right? Because I mean, by definition, but I think by definition, you can easily say that you can easily see this, right? Because if your FR belongs to A, and if your FR belongs to A, and your FR is 0, then you will definitely get this. You will definitely get this fact. So this is trivial, right? But conversely, it's not trivial, right? So you need to prove the other directions. This is difficult. So I will leave as I will leave it as next videos. Okay, and number 5. Number 5 is just what I said. If you take subset of this AKN, and then you can take the polynomial, it vanishes, and then take the 0 sets, it will be the closure of Y. Okay, this is easy to this can be easy proof. Okay, so notice this. Okay, so we can take the closure. We have this. Okay, notice that this guy is by definition is closed, right? In the Zariski topology, because I of Y just the closed set definition is just the 0 locus, 0 of some locus. Okay. 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 So now if you take W to be closed set, which is contain Y. Okay, which is closed set, right? So I can write Z of A is, let's say this is W, A is some ideal. Okay, so now Z of A is Y. So I can take the 0 set. So I will have this. Okay. Okay, and that is will be this, right? This is also trivial. But notice that okay. So now what we have W equal to ZA cover Y, and then we have A the subset of IZA cover I of Y. So what you have is what? You combine these two. Okay, then you get, so W is Z of A will what? Will cover ZIY. Okay, why this is true? Because you can see this, right? If you take Z, you get ZI of Y is a subset of Z of A. Okay, so you said if you take a closed set and it will contain Y, that closed set will contain Z of Y. So the closure is the smallest closed set containing Y, right? So which proves that this guy is actually Y. So smallest closed set, right? So this guy is actually cover this, right? Okay, so this is sorry, it's this. Okay, so this proves the results, right? Because the closed set is the smallest set which containing Y. So whenever any closed set cover Y, then we prove that that closed set must contain Z of I of Y. Because Z of Y is basically a subset of Y bar. Okay. Okay, so this will give you the this by combining this previous here Reynolds ansatz, then we have the following correspondence. Okay, so this correspondence is what? So we have this correspondence. So we have, if we take the Z of Y, and then we take this, and we will get so this, if we take A, then we will get square root A. If we take this, then we will get Y bar. Okay, so this tell you that this tell you the one-to-one correspondence between the algebraic set. So between the algebraic set in AN and so since we take algebraic set, right? But these corresponding to radical ideal. So corresponding to radical ideal. Okay, so simply speaking is that if somebody give you Y, then you can map the I of Y and then map A to be Z of A. Okay, so this is the first correspondence. So algebraic set corresponding to this algebraic set corresponding to radical ideals. Okay, and the second correspondence that we want to say is that irreducible. So remember that previously I had defined an irreducible closed set. So it's like if you can write as two proper closed set, it's called not irreducible. If you cannot write, then it's irreducible. Will corresponding to the prime ideals. I think this is the most important part. Okay, so what we're gonna to show is that we want to claim. So our goal is I want to claim that if y is irreducible, then I of y is prime. Okay, and I want to also prove. I also need to prove that if I of y is prime. Sorry, if I take y is prime, I take the a is prime. Right? I take the z of a should be irreducible. Okay. 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 So now y. So now let's start proof. Suppose y is irreducible. Okay, and then we want to show that I of y is prime. So I of y is the y is a set, right? Y is a set in the Zariski topology. So some points, and I of y is all the polynomials such that this polynomial, all the roots will satisfy this. Will be the roots of the polynomials. Okay, so this is simple. So in order to prove it's prime, just let me just recall. If x, y belongs to P, x belongs to P, or y belongs to P, then we call these P's called prime ideals. Okay. Okay, so let's say Fg belongs to I of y. Then what? Then by definition, right? So y will be subset of z of Fg. Okay. By previous I just proved, or in the previous video, that by the way, so Fg belongs to I of y means that every point of y, Fg will vanish on it, right? So y will be subset of zero locus of f of g. So it's zero z of f, union z of g. Okay, so now y can be written as z of f intersection y union y intersection z of g. Okay, y is irreducible, so these are close, right? Because I need to so I should say y is algebraic. Yeah, so only algebraic sets I define irreducible or not, so y must be close. So these guys close, these guys close, right? But they are proper. So either, so since y is irreducible, so either z of f union y is y, right? Or z of g intersection y is y. Okay, but either these will give you y is a subset of z of f. Okay, so or y is a subset of z of g. So if y is a subset of z of f, which means that f belongs to I of y, right? Because all the points on y is satisfied by the equation f, right? So equation f must be I of y by definition. Okay. So also this will give you either g of belongs to I of y. So we prove that the I of y is prime. Okay, I of y is prime. Okay, so conversely, as I take P to be prime ideal. Okay, and I say that I calculate the locus, right? And I want to prove that this is irreducible. So y1 union y2. Okay, so now I can take the I, right? I take the I both sides. Okay, and this z of p by definition is square root of p, but the radical of p for prime ideal will be p. Okay, so p. Okay, so p is I intersection y1 and y2. So what the hell is going on? Okay, so it tell you what p is a two intersection. P is a two intersection of two ideals. So either what? So either p of, so using algebra, right? P is a prime ideal, which is intersection of two ideals. So P must be I of y1, or P must be I of y2. Okay. This proof, yeah, I think it's not difficult. You can try to. I think this is just the algebraic fact that I think it's not difficult. Let me think. yeah, if you take any prime ideals, which is intersection of two ideals, that either it must be either one of them. Yeah, it must be either the same as one of them. Yeah. Okay. So which give you the proof, right? Because now it's irreducible. If it can be break into two, right? Then these two cannot be proper, right? Because P equals I of y1 or P equals I of y2. So you get Z of P just y1, right? You can take the Z part, right? Then you take a Z part, it become y1 bar, right? But by definition, y1 is closed, right? So it's y1. So okay. So which prove that either y1 is ZP or y2 is ZP. So which tell you that Z of P is irreducible. Okay. Okay. So example. So A to N, the whole space is irreducible because it corresponding to zero ideals. So zero ideal is prime. Okay. But notice that zero ideal is not maximum ideal. Okay, so now let's consider more strange examples. If you take A to be two-dimensional and F to be some curve, some polynomial, two variable polynomial curve, and then suppose F is irreducible, means that F is a prime ideal. Then the zero locus of A, right? Zero locus A will be irreducible, right? So Z of F will be irreducible. So it's amazingly that this irreducible is the same language as irreducible. Okay, now this is called a fine curve. Okay, so simply speaking is that if you take the complex plane and you can draw some stupid curve, maybe draw some curve. This curve may be some polynomial, the root of all the roots of some polynomials. That polynomials itself, that all the point itself is closed in the under list and it is irreducible. Okay, and notice there is an example. Yeah, I didn't say this before, but if you start on polynomial ring, then you can ask what is the maximum ideal. Maximum ideal. Okay, obviously that this is also another theorem of Hilbert-Nusselt ansatz, is that all the maximum ideal of this multivariable polynomial ring must be a point. So maximum ideals must be generated by x minus a1, x minus a2, x minus a3, x minus a. So these are all the maximum ideals. Okay, so which tell you that the maximum ideals corresponding to a point, and the points corresponding to maximum ideals. Okay, so we have the following beautiful diagram. We start from A, K, N, and then we map to K, X1, Xn. So the general algebraic set. So if you start from a closed algebraic set, if you take a Z, go here. Sorry, this is I, take Z. This will corresponding to radicals. If you start from a closed but irreducible set, it will give you the prime ideals. Okay, so if you go to the max, if you go to the maximum ideal. Okay, so you can see that if you go to the maximum ideals, it should be here. Okay, bad notation. So if you start from the maximum ideals, then what? Then you get a point. Okay. So what you're seeing is that when this points the set decreasing, the ideal grows. Okay, so this is a beautiful correspondence. Okay. Okay, so now we can but there's an idea called dimension theory. So probably in the next video that I will describe. Okay, so now let's take the definition or the coordinate ring. This is not difficult because let's say you take Y to be algebraic set. Okay. Basically fine. Oh, by the way, so okay, yeah, I think I previously defined a fine variety. So fine variety is a irreducible algebraic set. Irreducible close irreducible algebraic set. So it's, let's say take Y as a fine algebraic set. Basically, since it means that Y is a Y is the zero locus of some polynomials. Okay. Right. So so you can let's define a coordinate ring to be coordinate ring to be just right. So Y is algebraic set, right? So Y is a subset of this. So you can take I of Y, right? You can go to I of Y. So you can define a coordinate ring to be the polynomial ring x1 up to xn divided by quotient I of Y. Okay, so some people will write as A of Y. So this is usually denoted A. Okay. So this, yeah. Okay, so this is algebraic set. So algebraic set not need to be reducible, but for variety it must be reducible. Okay, so if Y is an affine variety, okay, means that means what? Means that Y is irreducible. So it means that I of Y is prime. So which tell you that coordinate ring is integral domain, right? This is the algebra, simple algebra, right? The field, the quotient prime ideal is will be integral domain. Okay, and there's a thing that I want to say is that I of Y is a finitely generated K algebra. Okay. This sentence is hard to define, so I will not tell you the definition, but I just want to say something. Okay, so now I think this is, yeah, so this is good starting point, but let me just give another definition, which is also important. So a topological space, is called a Noetherian if for any sequence, by the way, these are closed subset, then you must then there exists n such that Y of n equals Y plus 1, Y of n plus 2. This is called descendant condition. So this is the same as when you talk about ring, right? When you talk about there's an idea called Noetherian ring. So compared to the Noetherian ring in algebra, right? You have the descendant, you have the ascending chain. Okay, so this is in the algebraic, in the topological. You can define a Noetherian topological space, which is similar to the commutative ring. Okay, and so there is a theorem that I will not go to prove it. It's called the Hereby Theorem. So if R is there is a theorem. If R is Noetherian for a commutative ring, then one can show that R of x1, xn is Noetherian. Okay. Okay, so we will use this fact in the next video. So next video, I will describe the irreducible. This one can prove that the algebraic set can be written as uniquely as the union of irreducible varieties. Okay, and I will also talk about the dimensional theory in the next video. Then we will finish like the introduction to the finite varieties. See you guys.